Hello, everyone. Today, we're going to be going over Self-Taught Reasoner, which is a foundational paper in eliciting reasoning in large language models. This video, we're going to go over the paper itself and the core algorithm, along with any nuances within the paper to better understand and grasp how these large language models reason through tasks and have a better understanding of step-by-step reasoning and chain of thought. And the next video, we are going to implement this same algorithm in JAX and hopefully have some results to show for it and compare, basically run some ablations and build that project ourselves. But without further ado, I'm going to share my screen and we're going to go over this paper. And so the name of the paper is STaR, Self-Taught Reasoner, Bootstrapping Reasoning with Reasoning. And let's go over the abstract just to have a sense of what this paper is even talking about. Bootstrapping reasoning with reasoning might not make intuitive sense at first, but as we go over the paper, we're going to see that it's basically exactly what the title says. And yeah, so the abstract, here we talk about how generating step-by-step chain of thought rationales improves large language model performances on complex reasoning tasks. So chain of thought, to put simply, this was a concept, a prompting concept introduced, I believe, in this paper called Chain of Thoughts Prompting Elicits Reasoning in Large Language Models. I have it here. It's this paper right here, right? And chain of thought reasoning, or chain of thought prompting, is basically when you prompt the LLM to have a step-by-step approach to solving a problem. You see an example right here with standard prompting. When you input the question, which is all of this, right? You just get the answer is 11, right? You don't get that part where here, in contrast, it goes, Roger started with 5 balls and then 2 cans of 3 equals 6. And, it creates this chain of thinking that elicits better performance in answering complex problems, specifically related to math and a lot of logical focused things. And this paper came out, here it says January 2023, but in truth, that has to be an update, right? Yeah, it came out a few months before this paper. And basically what this paper tries to do is that it pushes that chain of thought from just a prompting technique, which in conversation doesn't exactly update the weights of a model, and the model doesn't internalize the knowledge throughout its training. It's not trained on that chain of thought reasoning. It is just in a conversation. This paper, what it tries to do is find a way to actually teach a model and have a model trained through backpropagation and updating the weights using this chain of thought rationale concept. And so they talk about it right here. Inducing large language model rationale requires either constructing massive rationale data sets or sacrificing accuracy by using only few-shot inference. That's what we were talking about, right? Like few-shot inference, which, by the way, few-shot is when inside the prompt you write, for example, instead of just saying solve step by step, and that's it, and then you give it the question, and then you prompt it to answer. Here you say solve step by step, and then you give a couple examples, right? So you give, this example of Mary had 4 apples, she buys 3. She buys 3 more. And then the answer would include that reasoning that you wanted to have. So you say She originally had 4 apples. Buying 4 more means adding, buying 3 more means adding 3 to the original. 4 plus 3 equals 7. Final answer is 7. And then you give maybe another example of that, and then you prompt it to actually answer whatever question is given. This example that you put within the prompt basically gives the LLM a good structure and a good rule to follow within its context window that it will most likely keep on following throughout. It's a lot better to do this than to just say solve step by step and then, giving it the prompt. And then here it says inducing model rationale generation requires constructing massive rational data sets or rationale data sets. This means large data sets that contain these actual reasoning traces. They say it requires constructing a massive one. That is very expensive, right? A human has to go in through a bunch of questions and basically, give me 1 second, go through a bunch of questions, right? And create a data set for the model to be trained on. Now, this all falls under what we call supervised fine-tuning, and I talked about it in my first video, in my first lecture in this series on reinforce. Supervised fine-tuning, this falls under this umbrella. And if you remember, one of the reasons we should start hopping into RLHF is that it's very expensive and very hard to create a massive data set. And so this paper proposes an algorithm that uses the actual reasoning traces of the model itself to, in a way, generate the perfect data set to then train itself on. And that's what bootstrapping reasoning with reasoning kind of suggests, right? You're using the original reasoning capabilities of the model to better learn how to reason in the future and then fine-tune it on that. This is what they call self-taught reasoner, STaR. It relies on a simple loop. You generate rationales to answer many questions. So we're going to go more into the methodology once we get there, but just think about, we have a data set of questions and answers, and we prompt the model, as we did here, to generate some rationale, some reasoning for the answer. Usually these data sets are very arithmetic heavy or just mathematically grounded, since that is something that requires a lot of logic. And here we prompted with a few rationale examples. If the generated answers are wrong, they try to generate a rationale given the correct answer. I'm going to go more in depth on that. And then the more important part, or just the final step, they just fine-tune all the rationales that led to the correct answers to a new model, and then they repeat that little loop. This method basically improves performance on multiple data sets in a way that larger models didn't. And it kind of opened the doors to a lot of thinking on how we improve reasoning in large language models. And so I'll go over this very intuitive graphic here. But basically in this paper, like I said, they bootstrap the reasoning ability to generate high quality rationales and repeat that. This process, you're going to see in the algorithm, works kind of like this. You give it a few shot prompt it, and then you give it a question. Like I said, question, it's like the Mary question, 4 apples, whatever, and then answer. The reason reasoning is needed for these arithmetic problems is that fundamentally a transformer, what it does is predict next token out of previous tokens. And so there isn't although it has large language capabilities, there isn't this built-in mathematical thinking into it. You have to figure out a way to prompt that. It's not going to automatically, just because maybe in the data set it learns that simple math, but then if you give it harder math, it's not going to, originally, it's not going to solve that problem correctly. So that's why you need these chains of reason where it kind of adds to its context window. Okay, Mary has 4 apples. If she buys 3 apples, that means she is adding 3 apples to her original amount, and they can step by step their way into that. We have a data set filled with these question and answer pairs, and what we do is we prompt them to reason through. So we iteratively go through the whole data set. Question 1, it reads the question, and then it's supposed to produce a reasoning trace that leads to a predicted answer. And what we do here is we check if the predicted answer is equivalent to the actual answer, then what we do is we save this as kind of an updated data set of this question, rationale, and answer, like tuple, you can think of it that way. So that in the next step, what we do is we fine-tune the same model, the base model, we fine-tune it on this data set. So then it starts explicitly learning reasoning, or learning to reason to achieve an answer. And one thing that they do in this paper, actually, that is very important, is that they introduce rationalization. Because here you might be asking yourself, okay, what happens if they predict the answer wrong? It's like a wrong answer. You can't really use, or you can assume that you can't use this rationale for that, for the data set, because it produced the wrong answer. So what they do is they introduce rationalization, because they found that without rationalization and just straightforward, you're going to slowly compress the data set, and it's going to lead to overfitting. It's going to lead to lack of generalization and things of that nature. So you want to keep expanding the data set somehow, right? And so their solution to this was, if the model produces the wrong answer, we do an additional step where we give it a hint. So we give the model, for all the questions it got wrong, we give it the question, and then we add a hint in which we already give it the answer. So it doesn't have to predict the answer anymore. It already has the answer. And then given the answer and given the question, it has to work backwards and kind of create its own chain of thought, kind of reverse engineering rationalization. And that way, even if the model gets an answer incorrect originally, it results in some kind of win for the data set, so that in the next step, it fine-tunes on this reasoning trace that it did not have before. And so you can think about it iteratively, step by step, or iteration by iteration, right? Every time we fine-tune the model, what we get is, even for the questions that it originally got wrong, we supply it a reasoning trace that results in the correct answer anyways. So this is a very efficient way to just expand the data set from its original question answer state to this question rationale answer state that we can fine tune a model on and then induce reasoning. That's what rationalization is. We'll talk about it, they talk about it here. I'm right here. We've thus developed the self-taught reasoner, a scalable bootstrapping method, allowing models to learn to generate their own rationales while also learning to solve increasingly difficult problems. They repeat the following process. Each iteration, they construct the fine-tuning dataset by attempting to solve the dataset using the current rationale generation, so the current ability without being fine-tuned or anything. And then they augment this dataset. Like I said, they expand it. The dataset's made a lot better, a lot higher quality. using what we called rationalization, where they justify the answers to problems. And so when they applied this on arithmetic, math word problems, common sense, all these things that require logic that us humans can solve because we have that internal thinking and that critical thinking in place, it yields these results that are comparable to just a fine-tuned model on a specific data set that is 30 times larger. So with a smaller data or with a smaller model, you can achieve comparable performance to larger models. And at the end of the day, that's the whole concept, or that's one of the bigger concepts and reasons within reasoning, is we want to save costs. We don't just want to scale, but we want to have a model that can think step by step and through that infer and solve problems. And here they talk about the contributions. They propose bootstrapping, like we talked about. And then, to me, the second, probably more important part is rationalization. And that's where the model is tasked with justifying the answer. Again, given the answer and the question, but given the answer as a hint, it's not meant to predict the answer. It starts chaining the reasoning backwards. And it's like, okay, given this question, given this answer, what would the proper reasoning be to lead there? And we can jump straight to the methods. So here they're talking about STaR without rationalization. You see this very probably like denser than should be, or mathematically denser than should be things. But what this is basically saying is that they have an initial data set of, so the data set is equal to X and Y pairs. That's literally the question and answer. And what they do is they have a small prompt set P of examples with intermediate rationalization. P equals that, where P is largely this double less than sign means largely less than the data set. This is basically the few shot prompting. They're saying, like, let's use this example of 10. They're saying that in the main prompt, they have, relative to the data set, let's say the data set is 100,000 question answer pairs, they have 10 question answer pairs as an example. And then that's in the main prompt. And then again, the model is prompted to answer whatever the original question is. And what they mean by this, the new data set is XP. You see right here, XP or whatever. It just means that they append to the question, to just the question prompt, they also append the main, like this fine few shot prompt. And so you have, instead of just the question from the data set, you also have the few shot examples. You add these together to have a new X. What do they have? XP. And then using this, think about that as input to the model. We have our model predict Y hat, which is the predicted answer. In the Mary question, right, we had the question, the answer was 7. We have our model try to predict that answer. And then we fine-tune the base model M on this filtered data set, and then restart this process by generating new rationales with a newly fine-tuned model. And they keep repeating this process until the performance plateaus. So if you're looking for actual, think about this. This is literally just a big for loop. They're saying until performance plateaus. That is a very subjective kind of way to look at things, in a way, right? I guess what they would mean by this is that they're measuring the validation loss, and when the validation loss doesn't stop or doesn't drop, drops less than 0.05, the drop is less than 0.05 for like 2 steps, then they just stop. So you're not going to see like a set like, okay, for 5 iterations, for 50 iterations, for 500. You're not going to see that. They do it here until performance plateaus. And important to note that throughout this whole process is that once a new data set is collected, so that's at the end of each iteration, they train the original, or they train from the original pre-trained model. and they don't train from the last iteration. We're going to go over this more concretely when we look at the algorithm, which is the most important part of this paper, and then when we talk about this graph up here. And so going further along this methods section, we also have this right here. Now, in my opinion, this is kind of stabbed in, but because they don't really go more in depth onto this whatsoever. But here they talk about how STaR, in a way, can be seen as an RL-style policy gradient objective. What does this remind you of? All of these equations here, what does this remind you of? This J, this is the reward, right? Last lecture, we talked about reinforce. And it's basically, this paper is basically saying that you can view the reasoning step, which I'll have as R. You can view the reasoning step, hold on. You can view the reasoning step as kind of a latent variable. And that means that there is a probability that a rationale is produced given the input, or there's a probability that an answer is given the input and the rationale for it. And basically, what reinforce does, if you remember it, uses this external signal, the reward, to push the gradient, or to generate gradients and push the weights of a model further towards increasing that reward. And here, this means that if you style this as a reinforcement learning problem, if the prediction, y hat, the prediction is equivalent to the actual answer, then you are given +1. Otherwise, you're given like +0. And in a way, right, the whole goal is to increase this reward when you are looping through and fine-tuning. And that's kind of what they mean, that this can be seen as a policy gradient objective. Let's read this here. STaR approximates J by greedily decoding samples of R hat and Y hat to reduce the variance of this estimate. So when they say greedily, they mean that basically they choose an answer, or they choose the rationale that led to an answer given that the answer was correct. So they're greedily just picking, if the answer was correct, we're going to use this reasoning to kind of update our model. And we'll talk about maybe some issues in assuming that later, but yeah, that is the kind of RL style, or the RL approximation here. They don't really go more into it. They literally say future work should investigate the link. And yeah, I mean, I guess it's grounding for future work. Remember, this is a foundational paper, right? This is like very novel at the time, May 2022, maybe, whenever it came out. And here they talk about rationalization. Like I said, they provide the answer as a hint to the model and ask it to generate the rationales in the same style as the previous rational generation step. And then given the answer, it reasons backwards. And this is something that they apply to the problems where the model solved or didn't solve the answer correctly. And yeah, there was something I wanted to talk about here. Maybe I'll go into it when we talk about, when we kind of pick apart this paper a bit, but let's look at the algorithm. I'm sorry, so the algorithm here, keep in mind these blue steps are the rationalization steps, R and R. These two are rationalization. Remember, this is something that they implemented after the original approaches, which is where they add the hint and then fine-tune from that. And yeah, so first thing they do is they make a copy of the original model. This is what gets fine-tuned. And then for n, lowercase n in 1 to n, capital N, remember there is no set constant n. This constant is that performance plateaus. And I hope plateaus was spelled properly, but it's just all the way to performance plateaus. What they do is they sample. This means that for every, or for each sample, Q&A sample in the data set, they generate some rationale and some answer, or some predicted answer. If the answer is wrong, what they do, if the answer here was wrong, what they do is they add a hint. So they give it the answer, they give it the question, and then it's supposed to generate the reasoning backwards. And so what we do is, after we do those 2 steps, we literally we fine-tune the original model, not this copy, but this original model. We fine-tune from that model the new data set. The new data set that contains the question, reasoning, and answers from step 3s and step 4. And then once we fine-tune that model, we redo this, right? We take that model, this model right here, and we sample a chain of thought reasoning and an answer prediction, and then we rationalize it, and then we do that a couple times, and that corresponds to very good performance. You see that here more clearly. You're given a question, right? You give the model a question, and it generates some rationale. Remember the chain of thought. And this is the pair that we output. If the answer is correct, then we just append it to this queue. We append it, the question, rationale, and answer, and then we fine-tune the model on it. However, if it's wrong, then we give it that rationalization hint. The hint is now we give the model the answer, and it has to work backwards towards the question, which generates, again, some rationale, which we then add again to this QRA. And this is the whole loop. This is where the for n in 1 ... n comes from. It's literally this part. This graph is very intuitive. It just, you understand it completely off this. And what this algorithm resulted in was, I want to show some of the numbers that they had, but I guess going into their experimental design, they used GPT-J, and since like the fine tuning and everything was like in an open source repository and yeah, publicly available, and it was a large model, 6 billion parameters. Something that they found is when you have a small model, you're not going to even get the reasoning traces in the first place. So this is a very important step, I guess, having an already smart enough model. They generate a data set of 50K randomly sampled questions, 10 random few-shot rationale examples for the prompt. And yeah, they used a couple data sets, CQA and also grade school math 8K, GSM 8K. Which, when we implement it, I would love to test on this data set and train on this data set. But regardless, some of the numbers they found, as the iterations went on, this is without rationalization. So without basically discounting the wrong answers, you can see that the model takes more time to learn given the complexity of the question. Meanwhile, with rationalization, relatively quickly, you see the models jump. And don't get fooled by the graphs alone, but look at the range, right? look at the scale of iterations, upper bound 28, lower bound 0, here 0, 16. So by iteration 4, look at the, let me use a different color. Look at, by iteration 4, kind of how much the models had improved. And then here by iteration 4, you know, we still have 0% for 5-digit summations. And yeah, that did not start improving until 24. However, here it was already improving from like iteration 2. And yeah, you guys can go more in depth on the actual evaluation and how they evaluated this, but here let's see this part of GPT-3 with direct fine-tuning with a specific data set. They use CQA again. It got 73%. GPT-3, I forget, but I believe it's like 150 billion parameters, GPT-3 size. Let's see. 175 billion parameters. And they, with GPT-J, which was 6 billion parameters, and rationalization and this STaR loop, they approximated the same accuracy with less of the training data being used. And that is a big finding for a model 6 billion compared to 175 billion. I don't know the math on that. They say 30 times. Yeah, it makes sense. That's why they say 30 times, because it approximates this accuracy just with 6 billion parameters. Now, going into discussions, here you could see more what they talked about here with the responses or with the findings. But let's go into the discussion of this paper, some challenges. Fundamentally, we have to discuss some of the assumptions that they made in this paper, explicitly rationalization. So again, an essential question is the role rationalization plays. But for this whole system to work, they bet on the fact that, and the very intuitive fact that if you give someone a question, or if you give a model a question, here's our model, and it generates the reasoning and answer, and the reasoning is wrong, we are counting on the fact that next time, what we should do is we should feed the question and the answer and prompt the model, instead of trying to solve the problem, try to find the reasoning that led to this. And so this idea that a model can reverse engineer reasoning is something that they bet on and they won. It showed and it proved through empirical study. Rationale. Something that they proved in this paper. And honestly, more important than the STaR loop itself is this finding of rationalization. Now, another kind of assumption made in this paper that doesn't quite stand the test of time, or the kind of, I guess, jumps to a conclusion, is the fundamental idea that given a question and assuming that the answer is correct, that means that whatever the reasoning was is correct reasoning. But you guys can see that that is a pretty big jump in conclusion. And also same thing, that a question resulting in wrong answer doesn't mean that the reasoning is wrong. It could mean a lot of different things, or there could be good signal within the reasoning that led, or that could be useful in future iterations. However, we kind of just discard it and then work backwards. If we go past the appendix, right? We go here into some error patterns. You see this assumption is kind of tested. For example, here, they graded this rationale as not being helpful. Same thing here. And this question, for example, the answer must be in a place where someone can gain knowledge other than score from text. The answer is a meeting. Like, what's it talking about? You know, so, but in some of these, that reasoning could lead to correct answer, and you're not even checking the value of the reasoning. This is something that is tested nowadays with the emergence of PRMs, which are, instead of just grading the output, we grade the reward or the reasoning steps. So it's called the process reward models. This is something we're going to touch on by the end of this series. But it's important that you guys note that. And as we come to a close on this paper, we're going to implement this in a future video. I'll get that to you guys by the end of the week, or by the end of the weekend. But what is STaR fundamentally? STaR is a fine-tuning technique that uses a model's own reasoning. Model's own reasoning to create kind of the perfect data set to later fine-tune and iteratively improve the model on it. And this, in theory, and then now in practice, this increased the reasoning capabilities of the model after being fine-tuned on a data set created by its own reasoning. And thus, that's what they mean by bootstrapping reasoning with reasoning. It's like you have original reasoning and you want to create better reasoning. You kind of just add more reasoning to this data set. Again, remember the importance of rationalization. That's probably the biggest takeaway from this paper. The rationalization part, the importance of adding the hint and reverse engineering the solution, which leads to a good chain of thought link that can be used again, even if the model originally got the question wrong. And again, this is something that we will be building next week or in a couple days. It's, as you can see, the main implementation is this algorithm right here. The rest of it is just some engineering scaffolding around this loop right here, but this is the most important part. And it is a very straightforward loop. Okay, that was bad. Very straightforward loop, which we will implement. And yeah, but it provides a good foundation to the future of reasoning in models and how models and training is approached to induce this reasoning. But I hope you guys enjoyed, and I'll see you guys for the next one.